Hello students, this is the final part of electromagnetic reflection or refraction, and today we will see the dynamic properties of electromagnetic wave after reflection or refraction or transmission. In this video today I will try to put the things in order quite differently. In the earlier videos I calculated live in the video, but today I have seen that in this portion of the syllabus most of the things are casual mathematics. You have to solve some algebraic equation to get the final result. Without concentrating on the equations and the algebraic calculation, better I thought to concentrate on the physical part of the problem. The problem is the electromagnetic wave is propagating from a particular medium. Let us consider it is medium 1. Medium 1 is characterized by epsilon 1 and mu 1. These are permittivity and permeability. Medium 2 is characterized by epsilon 2 and mu 2, permittivity and permeability. As the previous video where we concentrated on the kinetic properties, I am considering the similar thing, that Ki is the wave vector of the incident wave and it is propagating towards the interface, where the interface is situated at z equals to 0 plane. This is x-axis, this is z-axis, so this plane is z equals to 0 plane. So this type of interface is here. This is the interface and this is the plane of incidence. The plane of the paper is the plane of the incidence and perpendicular to that this is the interface. The interface is differentiating these two mediums, where the incident ray and the reflected ray both are traveling in the medium 1, whereas the transmitted ray or the refracted ray, it is traveling in the medium 2. So their characteristics should be different. As we wrote the equations of the electric field and magnetic field the last day, for the first the incident ray, I have written the same thing. The incident ray that may be characterized as EI equals to E0I e to the power I Ki dot r minus omega I into t. This is the time dependent part or phase part. This is the space time equation. The equation contains both the space and time. From the electric field, if we calculate the magnetic field, we can write the equation like that: Hi equals to K cross E divided by mu omega. Why? Because from the electromagnetic theory we have seen that K cross E, that can be written as K cross E is the transverse nature of electromagnetic wave, was equals to mu omega H, that we have seen. So following this equation I have written the value of H. H will be equals to K cross E divided by mu omega. So Hi will be equals to Ki cross Ei divided by mu 1 omega I. What is omega I? Angular frequency of the incident wave, and mu 1 is, that is the permeability of the medium 1. Similarly for the reflected wave, if you want to write the equation, it will be Er equals to E0R e to the power I Kr dot r minus omega r into t. Hr will be equals to Kr cross Er divided by mu 1 omega r. What is omega r? This is the angular frequency of the reflected wave. Now in some books you will find that instead of omega r and instead of omega I, only it is written omega 1. That is, they have considered that the angular frequency of the wave while traveling in the medium 1 is omega 1. And similarly for omega t, instead of omega t it is written omega 2. That is, they have considered that when the ray is traveling in the medium 2, its angular frequency will be omega 2, nothing else. For the transmitted wave you can write Et equals to E0t e to the power I kt dot r minus omega t. That is, E equals to E0 e to the power I k dot r minus omega t, this equation. Ht equals to kt cross Et divided by mu 2 omega t. So these are the three equations of electric field and magnetic field separately. For incident wave, this is the incident wave; for the reflected wave, and for the transmitted wave, this is for the transmitted wave and reflected wave. This is as simple as before. We have done it already in the previous video. We have understood it already also. So let us proceed now we will be calculating the dynamic properties. That is, we will try to calculate the reflection coefficient, refraction coefficient, and relationship between them, etc. So in the dynamic property, we have to consider 4 cases. Actually not 4 cases, there are 2 cases, and both the cases will have 2 sub cases. As a whole, we have to consider 4 cases. I will solve the case 1, problem 1, case 1 totally. Then I will show that in the same procedure you can solve other problems. How the 4 problems are generating? The 4 problems are generating from the type of incident ray. First, I am considering that incident ray is having some electric wave vector, that is the E, electric field, direction of the electric field. What is the direction of the electric field vector for the incident wave? This may be of 2 types. First, you consider this is the interface. Okay, this interface is just the perpendicular on the surface. This is the interface. This type of interface is there. Okay, so once you consider that this is your interface and the electric field is tangential to it, and you can this is perpendicular, and you can consider it is tangential to it. That is, the electric field, once you are considering electric field is perpendicular on the plane of the paper, and once you are considering it is on the plane of the paper. If it is on the plane of the paper, then it will be perpendicular to the interface, and vice versa. If it is perpendicular to the plane of the paper, then it will be tangential to the interface. You understood? So first I will consider a particular case where I am considering case 1, that E is perpendicular to the plane of incidence. The plane of incidence, we have considered the plane of paper is the plane of incidence. This is the plane of paper, this is the plane of incidence. I am considering it is perpendicular to the plane of incidence like that. Like that, the electromagnetic wave vector is propagating. So the boundary surface or interface is like that. So if it is perpendicular to the plane of the paper, it will be tangential to the boundary. So like this, it is propagating, it is tangential to the boundary. So that's why I have written first that if E is perpendicular to the plane of incidence, E is tangential to the boundary. If E is tangential to the boundary, the continuity of the electric field across the boundary demands this equation. I can write this equation as equation 1. Demands this one, E0I plus E0R equals to E0T. This equation we have considered the last day also. Probably you will remember. This is from the continuity of the tangential component of the electric field across the boundary. The component of E0I plus the component of E0R will be equals to E0T across the boundary. That is, the incident ray plus reflected ray will be equals to the transmitted ray across the boundary. Now, if the electric field is tangential to the boundary, from the tangential component of magnetic field, it demands this equation. Why? Because if I go back to the diagram, I am going back to the diagram again. This is my diagram. Now I am considering this equation. How E is propagating, I have considered E is perpendicular to the plane of paper. E is like that. E is perpendicular to the plane of the paper. E is propagating like that. So what will be the direction of H? We know in electromagnetic field that E and H propagates perpendicular to each other. So H is on the plane of the paper. So if H is on the plane of the paper, then H, component of H along the surface. So this is theta I. So its cos component, but theta R, its cos component will be in different direction. So I have to convert this direction along positive x-axis. So theta R will have the negative cos theta, and theta T will be have the positive value. I am writing, last day we have written the same equation. Probably you will remember that H0I cos theta I, cos component along positive axis. Its component, cos component is along negative axis. That's why I have taken another negative sign, so that I can have the cos component along a particular direction. H0R cos theta R equals to H0T cos theta T. I can name it equation number 2. Now you look at equation number 1 and equation number 2. There are some similarities. This is the tangential component of electric field across the boundary, and this is the tangential component of magnetic field along the boundary surface. Now I am considering the subcase. The subcase 1 is, I am simplifying the problem. I am simplifying the problem in one line, writing the for normal incidence. If I consider for normal incidence, theta I, theta R, theta T all will be 0, and if you put cos 0, all will be 1. So this equation will be very much simplified, and these cos components are vanishing. The equation is H0I minus H0R equals to H0T. I can give it equation number 3. Now look at equation number 1 and 3. I can convert the H in terms of E. How? Because in the just before some time I have written this equation, that is, you have already seen that from the perpendicular component of E and H, you have already written previously. I am showing it here, that is K cross E, that is equals to mu omega H. This equation you have seen, and also you have seen H cross K equals to epsilon omega E. So if you take only the scalar component, do cross multiplication, you can generate the relationship between E and K. K will cancel both the sides. You can generate the equation between E and H, and the equation demands that E equals to whole root over of if you divide these two, K cancels out, and here you are having, okay, I am doing the steps for you. In this side you are having E by H equals to omega cancels out, mu by epsilon, H by E. So you can write E by H equals to whole root over of mu by epsilon, isn't it? This is very simple. So instead of H, what I can write? Instead of H, I can write whole root over of epsilon by mu into E. That is what I am writing here. Instead of H, I am writing whole root over of epsilon by mu into E. So for H0I, I should write H0I is for the incident ray. For the incident ray, it is traveling in the medium 1, so it will be epsilon 1 by mu 1 into E0I. This is reflected ray, this is traveling also in medium 1, for this one also epsilon 1 by mu 1 into E0R. H0T, this is transmitted ray, it is traveling in medium 2, that is why epsilon 2 by medium 2 mu 2 into E0T. Now I am giving it equation number 4. Now you look at equation number 1 and equation number 4. These are also having the coefficients of E0I, E0R, and E0T. It is also having the coefficient of E0I, E0R, and E0T. So you can simplify these two equations. From this equation 1 and 4, if I eliminate the value of E0T, I am eliminating the value of E0T from these two equations. So I will get the ratio of E0R by E0I. What the ratio tells physically? Physically, the ratio tells you the value of the electric field component of reflected wave divided by electric field component of the incident wave. And if you do so, you will get the relationship like this one: whole root over of epsilon 1 by mu 1 minus whole root over of epsilon 2 by mu 2, whole root over of epsilon 1 by mu 1 plus whole root over of epsilon 2 by mu 2. Now you can do the same thing from equation number 1 and 4. You eliminate the value of E0R, you eliminate this value E0R, so you will get the relationship between transmitted wave and incident wave. The relationship between transmitted wave and reflected wave will give you the relation that 2 into whole root over of mu 1 by epsilon 1 by mu 1 divided by whole root over of epsilon 1 by mu 1 plus epsilon 2 by mu 2. This is very simple, just algebraic formula. You have to proceed accordingly step by step. Now for simplicity, I am considering a particular medium where I am getting mu 1 equals to mu 2 equals to mu. That is, the interface, though it is differentiating two different mediums, I am having mu 1 and mu 2, both are same in both the sides. So for simplicity, if you write that, all mu 1 mu 2, these will be cancelled out, and the formula will be epsilon 1 minus epsilon 2 divided by epsilon 1 plus epsilon 2 for the ratio of E0R by E0I. and you can simplify, divide all throughout by epsilon 1. So we will get 1 minus whole root of power of epsilon 2 by epsilon 1, and here you will get 1 plus whole root of power of epsilon 2 by epsilon 1. Now you can generate, instead of epsilon 2 and epsilon 1, you can write eta 2 by eta 1. How it is possible? You can check it out. First, take the value of eta 2 by eta 1, that is the ratio of refractive index different between two mediums, eta 2 and eta 1. Eta 2 equals to C by V2, eta 1 equals to C by V1. This will be C by V1. So C cancels out, you are getting V1 by V2. Again V, the velocity, can be written whole root over mu 2 epsilon 2, and here it can be written as mu 1 epsilon 1, actually reciprocal of that. So if you take the reciprocal of that, finally you will get epsilon 2 by epsilon 1. So finally what I am getting, eta 2 by eta 1 equals to whole root over of epsilon 2 by epsilon 1. So instead of this epsilon whole root over of epsilon 2 by epsilon 1, I can write eta 2 by eta 1. So this will be equals to 1 minus eta 2 by eta 1 divided by 1 plus eta 2 by eta 1. Simplify this one, you will get this result. So this is the ratio of electric field component between reflected ray and incident ray, eta 1 minus eta 2 divided by eta 1 plus eta 2. Similarly, for transmitted ray and incident ray, you will get 2 eta 1 divided by eta 1 plus eta 2. Where from you will start? You will start from this equation, E0t by E0i. You have to take the, you will put mu1 equals to mu2 first, mu1 mu2 cancels out, divide all throughout by epsilon 1, then put the value of epsilon whole root over of epsilon 2 by epsilon 1 equals to eta 2 by eta 1. You will merge to this result. So remember these two results are very important. This is giving you the ratio of electric field component for reflected wave and incident wave, and transmitted wave and incident wave. So with these two I am proceeding further. What I am writing now, I am trying to calculate the reflection coefficient. What is reflection coefficient? Reflection coefficient tells you the energy of the reflected wave divided by energy of incident wave. This is the reflection coefficient. How to get the energy? Energy stands for electric field into magnetic field. Here also it is transfer the electric field into magnetic field. So I am trying to calculate the reflection coefficient. It is abbreviated as R. So first you have to calculate the energy of reflected wave divided by the energy of incident wave. So what is the energy of reflected wave? E0R into H0R. What is the energy of incident wave? E0I divided by H0I. So from this you can write this equation by simplicity. How I have converted this H in terms of E. How you can convert H in terms of E? H equals to whole root over of epsilon by mu into E. Like this I have transferred. So first what I have written, instead of H0R, instead of this H0R I have written E0R into whole root over of epsilon 1 by mu 1. So you can multiply this one with this. You have to write just epsilon 1 by mu 1, and here also for H0I, E0I whole root over of epsilon 1 by mu 1, because the reflected ray and the transmitted ray both are traveling in medium 1. So for simplicity I can write it, this will be cancelled out, and I am getting only E0R whole square divided by E0I whole square. Now I know the ratio between E0I and E0R and E0I. I have just calculated it. So putting that value, I am getting eta 1 minus eta 2 divided by eta 1 plus eta 2 whole square. This is the value of R. Remember this one. Similarly, you can calculate the transmission coefficient. How to calculate the transmission coefficient? You have to know the energy of the transmitted wave, that is E0t into H0t, divided by energy of incident wave, that is E0I into H0I. So instead of sorry, E0t and H0t, we can write whole root over of epsilon 2 by mu 2 into E0t, because transmitted ray is traveling in medium 2, and you can write E0I into E0I into whole root over of epsilon 1 by mu 1. So we have already considered that mu 1 equals to mu 2. So mu1 mu2 cancels out and you are getting E0t divided by E0i its whole square into eta 2 divided by eta 1 whole to the power of epsilon 2 by epsilon 1 will give you the value of eta 2 by eta 1, just the calculation I have shown you before some time. So after putting the values E0t by E0i you have already calculated, you will get this result. Now if you add this reflection coefficient, the value of r, and the transmission coefficient, the value of t, r plus t, you add these two, you will get r plus t equals to 1. It stands for that reflection coefficient plus transmission coefficient equals to 1, that is no energy is lost in between. From this equation I can prove the Stokes law that I have used in case of interference. That in interference I have told you, when the ray is traveling from the rarer medium to denser medium, then there will be a phase change of pi. So I can get the idea about the phase change now. Look at this equation. You have calculated just before some time the value of reflection coefficient. The value of reflection coefficient you have calculated, and the value of E0r by E0r, that also you have calculated. The ratio of the electric field of reflected wave and the incident wave. I am writing this equation, eta 1 minus eta 2 divided by eta 1 plus eta 2. So what I have written here, I have written only E0r by E0i equals to eta 1 minus eta 2 divided by eta 1 plus eta 2. I am considering that this is my medium interface, and this is medium 2 and this is medium 1. In the medium 2 the refractive index is eta 2 and here it is eta 1. I have considered eta 2 is greater than eta 1. That is, the ray is traveling from rarer medium towards the denser medium and getting reflected back. It is traveling from rarer medium to denser medium because I have considered eta 2 is greater than eta 1. Then what happens? You take the value E0r by E0i, always this value will give you the negative result, some negative quantity, that is minus 1 into something. So E0r and E0i are not in the same phase. The negative sign indicates they are out of phase, that is, there is a phase difference of pi introduced. Phase difference pi stands for opposite in phase. So hence prove the Stokes law. So if you remember, we were calculating the problem, that is, if this is my interface and I am having the incident ray, the electric field vector is E0i or EI, and I considered first that EI, it is perpendicular to the plane of interface. This is plane of interface. We considered it is perpendicular to the plane of interface. So it was tangential to the boundary. Now what we did, for simplicity of calculation, we considered theta I equals to theta R equals to theta T equals to 0. That is, we considered normal incidence. After considering normal incidence, these were our calculation. Now if we do not consider normal incidence, then what would have been the calculation? The calculation would have been a little lengthier, nothing else. In this case, theta I, theta T, theta R all considered was equals to 0. So if you do not consider them as 0, then the cos term will remain, and you have to calculate the whole thing considering the cos terms. The cos theta I, cos theta R and cos theta T will remain, and with that the calculation will be little lengthy than the previous one, nothing else. If you try this calculation, you will have some results. I am showing you the results what you are going to have with this calculation. You will get the calculation like that. First, if you calculate the ratio between the transmitted ray first you are calculating the ratio between reflected ray and the incident ray, E0i. You will get the result like that, epsilon 1 by mu1 cos of theta I minus whole root over of epsilon 2 by mu2 cos of theta t divided by whole root over of epsilon 1 by mu 1 cos of theta I minus whole root over of plus epsilon 2 by mu 2 cos of theta t. This will be the ratio between E0R and E0T, and if you calculate the ratio between E0T and E0I, this will give you the result 2 whole root over of epsilon 1 by mu 1 cos of theta I divided by whole root over of epsilon 1 by mu 1 cos of theta I plus whole root over of epsilon 2 by mu 2 cos of theta t. In between you have already considered that theta I equals to theta r. That we have already proved, and we have considered this one. So from that you will similarly calculate the value of reflection coefficient, you will calculate the value of transmission coefficient, then you can try proving that r plus t equals to 1. That is the thing. And also you can prove the phase change after reflection. This is very basic thing, and you can do it, I believe. And the next set of problem will be totally different, and in that problem we are considering that E is other case 2, where I am considering that the electric field vector E is parallel to the plane of incidence. Here also the calculation is almost similar. So if E is parallel to the parallel to the plane of incidence, then magnetic field component will be tangential to the boundary, and its tangentiality demands H0I plus H0R, that will be equals to H0T, and the cos component of the electric field vector will be continuous, that is E0I cos of theta I minus E0R cos of theta R equals to E0T cos of theta T. This will be the basic difference. If you remember, in the previous case when E was perpendicular to the plane of incidence, then E was tangential to the boundary, then this equation was with E and that equation was with H. That is, the cos part was associated with the magnetic field. Here the cos part is associated with the electric field and magnetic field is simple. Now what you have to do, from this equation you have to convert this equation in terms of E. So in terms of E, if you write this equation, then you can write it as epsilon 1 by mu 1 into E0I plus whole root over of epsilon 1 by mu 1 into E0R equals to whole root over of epsilon 2 by mu 2 into E0T. Now you are getting again two equations. This is one equation and this is another equation. From these two equations, once you have substitute the value of E0T, if you substitute the value of E0T, then you will get the relationship between E0R and E0I. You will get some result. Now as sub case, for simplicity of calculation, once you can consider it is normal incidence and you can eliminate the values of cos theta I, cos theta R and cos theta T, the calculation will be simple. In that case you can try calculating the value of R, you can try calculating the value of T, then you can put that R plus T equals to 1. For oblique incidence the calculation will be a little lengthy, otherwise almost the calculation will be as simple as before. And in this calculation also, suppose you are considering that you are proceeding first the simple case. The simple case is the normal incidence. For normal incidence, if you considering now first the normal incidence, the simple case, in that case after eliminating the values you will get the value of E0I, E0R divided by E0I to be as simple as before, eta 2 minus eta 1 divided by eta 2 plus eta 1. and you will get the values of E0 t by E0 I to be equals to twice eta 1 divided by eta 1 plus eta 2, and you can calculate the values of r will be equals to eta 2 minus eta 1 divided by eta 2 plus eta 1 its whole square. You can try calculating the value of t. The value of t will be equals to eta 2 by eta 1 into 4 eta 1 square divided by eta 1 plus eta 2 its whole square. And you can calculate the value of r plus t. The value of r plus t, you can try calculating this one. R plus t will give you the result 1. You can try this at home. This is very simple. And for oblique incidence, you have to consider the cos values. The cos values will remain as the previous, and with oblique incidence, if you do not consider the normal incidence, the calculation will be little lengthy, but it is doable. In that case, you will get the value of E0 r by E0 I. First I am showing the calculation of E0 r by E0 I for oblique incidence. When you are considering the cos values, the value of E0 r by E0 I, that will be equals to tan of theta I minus theta t divided by tan of theta I plus theta t, like this one. And the value of E0 t by E0 I, that calculation will be twice cos of theta I sin theta t whole divided by sin of theta I plus theta t cos of theta I minus theta t, like this one. And from that you can calculate the value of r, you can calculate the value of t for oblique incidences. The value of r for the oblique incidence, if you consider, it will be equals to tan square theta I minus theta t divided by tan square theta I plus theta t. And transmission coefficient, if you consider the transmission coefficient, this value will be four cos square theta I sin square theta t divided by sin square theta I plus theta t into cos square theta I minus theta t, like this one. So these are simple algebraic calculations. You don't bother much, just try, take your pen and draw the diagram very neat and clean. After drawing the diagram, proceed previously that I have shown you the approach in the first case 1, and try to do it your own. I hope this will not be very difficult for your calculation. Only one thing remaining, that is you can prove the Brewster's law from this equation. If you remember the Brewster's law that you have gone through in 12th standard, also in the polarization, it is that tan theta p equals to mu. This was Brewster's law, and the physical significance was like that if light is traveling from one medium to another medium, it is falling on the interface with angle of polarization theta p, then the reflected ray and the transmitted ray will be exactly perpendicular to each other, and the reflected ray will be plane polarized. I am trying it from this equation, the reflection coefficient, where I have considered that there is one interface. This is the interface, and now the E vector is parallel to the interface. E is parallel to the interface. This is the parallel to the plane of incidence. E is parallel to the plane of incidence. That is, if this is the plane of incidence, E's vectors are lying like that, parallel to the plane of incidence. It is traveling like that, and it is getting reflected. What I am trying to write, the value of r equals to tan square theta I minus theta t divided by tan square theta I plus theta t. So now if I consider the theta I plus theta t equals to 90 degree, if I consider this one, then what is the significance of that? The significance is, my picture was like that. This is the interface, this is the incident ray, it is incidenting with the angle theta I, this is theta r and theta I both are equal, so I can write it theta I also, and this was the transmitted ray, this angle was theta t. Okay, so we consider, if this angle theta I plus theta r or theta t, whatever you call it, if these two angles are 90 degrees, so in between this angle will be 90 degree, this will be 90 degree. So I can directly say that there is a transmitted ray and the reflected ray are perpendicular to each other. So half of the Brewster's law is proved now. So in this particular case, the reflected and transmitted ray becomes mutually perpendicular, and the particular angle of incidence is known as angle of polarization. So I will call it the angle of incidence, that theta I. Instead of it, I will write theta p, angle of polarization. Okay, so what will be the value of theta t now? Theta t, I have written already, consider theta I plus theta t equals to 90 degrees. So theta t will be 90 degree minus theta I, that is 90 degree minus theta p. I can write it like that. Okay, now apply Snell's law. If you apply Snell's law in the interface, you can write 1 eta 2, that is equals to eta 2 divided by eta 1, that is sine of theta I divided by sine of theta t. Try to concentrate. Sine of theta I divided by sine of theta t. Instead of sine of theta t, what can you write? Sine of theta I divided by sine of 90 degree minus theta p. So sine 90 degree minus theta p means cos theta p. So sine theta I divided by, theta I and theta p both are equal. Instead of this theta I, you can now write theta p. So sine theta p by cos theta p will give you tan of theta p. Look, tan theta p equals to mu. So this is nothing but Brewster's law. So from this electromagnetic wave theory, considering that electric field vectors are on the plane of incidence and it is perpendicular to the interface, you can consider that its magnetic field will be tangential to the boundary and electric field is not. And in that particular case, considering the reflection coefficient R, you can prove the Brewster's law of polarization. So this is the end of the reflection and refraction of electromagnetic wave. Remember, we have considered two cases, and both the cases were having two subcases. First case was that the E vector, it is perpendicular to the plane of incidence. We considered this is the plane of incidence, E vector was lying like that, and it was having two subcases. First, for normal incidence the calculation was simple, for oblique incidence the calculation was lengthy. Secondly, we considered that E vector is on the plane of the incidence, parallel to the plane of the incidence. In that case, it was having two subcases. The subcases were, for normal incidence the calculation was very simple, for oblique incidence the calculation was little lengthy. And for all the cases we can prove the Stokes law of reflection, that is, for reflection there will be a phase change of pi if the ray is traveling from rarer medium to denser medium. From this case also you can easily try it. that if you consider that for a particular case E0R by E0I, you are considering that eta 2 is greater than eta 1, the same thing you can prove. For oblique incidence also you can prove the same. So with that we conclude. In the next video we will try to start a new portion of electromagnetic theory, and that is it for today. Thank you.